Hey guys, BuildZoid here, and today we're going to be finally taking a look at the Z390 Phantom Gaming ITX motherboard because some very generous fan of AHOC actually went ahead and just bought this board for me to do a review of it. So now I have it. I've taken it apart. We're going to do a PCB breakdown, and then we're going to look at the BIOS, and I'll probably add it to my other motherboard test result charts, and I'll probably test VRM thermals as well. Anyway, so yeah, this is the board we're looking at, and this is probably the best Z390 ITX motherboard out there. Now, it's also one of the most expensive ones, and I said probably because I'm just kind of like I don't have the most positive experiences with Asrock's BIOS. Let's just put that that way, put it that way, because yeah. My experience, like with the X299 OC formula, it's basically like, well, it's just straight up worse than the X299 Dark when it comes to Skylake X. Admittedly, it's way better at KB Lake X than the Dark is. Like, the difference between the OC formula on KB Lake X versus the Dark is, I'd say, for most people, more than makes up for the fact that the OC formula kind of sucks on Skylake X. Yeah, you know, that's X299, so I'm not sure on these boards Asrock's BIOS might be better because these are just more mainstream than than the X299 boards, and you'd assume therefore they'd put more effort into the BIOS, or at least have the BIOS more refined over time. Anyway, today we're just going to mostly focus on the actual you know, physical build quality of the board, and I gotta say that, like with a lot of sort of high-end Asrock motherboards, I like it a lot. We'll get into it right now. Starting off with the V-Core VRM, which is this right here. So that's our V-Core. So that, of course, provides the majority of the power that the CPU will consume. iGPU power is provided by this lovely thing over here. So iGPU, which I couldn't there, VIGPU. Memory power is this right here. So that's our VDDR. Right there. Then we have this mess over here, which I didn't actually bother to identify which regulator does what, because these are all of the, these are the regulators where I kind of go like, oh yeah, this exists. It doesn't really have to do much work. It's not worth worrying about. So we're probably looking at I/O, system agent, and maybe PCH voltage. The PCH voltage, like the PCH VRM might be somewhere else on the board. This is one of the awkward things I don't like about ITX boards, is that they're so cramped that it's actually really hard to identify a lot of stuff. Because unlike an ATX board, right, the PCH is somewhere over there. So the PCH VRM is also somewhere over there, and therefore I don't have to include it when I see three random inductors right between the CPU and PCH, and I'm like, well, this might be PCH power. That might be PCH power. That could be I/O. That could be I/O. That could be, or yeah, so I'm not even sure on the groupings because I can't even identify these two chips right here. I do know that this is a fully integrated buck converter, but this could be a controller, or that could be a controller, or they could both be integrated buck converters. That would actually be more realistic, but anyway, you get the idea. This is a mess. None of those voltages really, none of those voltage regulators matter that much, so they exist. They're probably right there. That's where I'll leave it for now, because I haven't even gotten around to turning the board on yet. So that's our I/O, SA, and PCH stuff. And then on the back of the board, we have a whole bunch of, and GIMP is being very cooperative today, so I just had to do that. On the back of the board, we have a bunch of more regulators. So we have these right here, which are from Nuvoton, and those are, whatever. And those are NCT 3101s. And those are DDR termination regulators, except there's too many of them, as far as I can tell. I'm pretty sure you can't have different DDR. I'm pretty sure you can't have a different VTT DDR per DIMM slot on LGA 1151. So one of these is probably not for VTT DDR, and it's maybe for something like VCC PLL OC or VCC PLL or DMI PLL or you get the idea. There's basically a whole bunch of other. There's a whole bunch of extra voltages on LGA1151 that exist solely for the purpose of removing cold bugs and cold boot bugs when you're on liquid nitrogen. And one of those is probably handling one of those. Actually, maybe both of them are. And there's a VTT DDR regulator that's much smaller because, quite frankly, these are huge for just VTT DDR. And that might be buried somewhere in this area on the other side of the board. But, you know, the 24 pin's in the way. I can't see anything there, so... but these exist, and that's what they are. Then we have some more that I suspect are some kind of regulator. And these are RT7905s, but I can't even look these up. I can't get a data sheet for them, so I assume they're some kind of linear regulator, but I don't know what. Like what the spec on them is, or if they're even linear regulators. I'm just guessing that they probably are, because that looks like a linear regulator part number from Rich Tech. So anyway, moving on from that section, I think we covered all of the regulators on the back. Oh, that might be another 301. I mean 3101. So might be another one of those. But yeah, so there's a good chance that when we get into the BIOS, this will actually have all of the extreme overclocking voltages, which is kind of cool. Like, there's been some ITX motherboards, like there's been the Maximus 8 Impact. That thing was actually ridiculously popular for LN2 overclocking, but that thing had the advantage that 7700Ks don't pull anywhere near as much current as 9900Ks do. So, you know, it's like a bit of a different scenario there where it's like, okay, you don't need that much V-Core VRM to power the CPU properly. Where here it's like, well, a 9600K would be fine, but most people don't want to run a 9600K on LN2 in the first place. So, yeah. But it might still be able to do that, and it potentially would be a great board for, like, benchmarks that benefit from having a 9900K's memory controller, but don't benefit from having 8 cores, right? So, that kind of thing. So yeah, that'll be interesting to see how many voltage options we get in the BIOS, because looking at how many random voltage regulators we have around the board, it looks like it should cover all of them. So, and this is another one of those NCT 3101s over here, and well, that covers all the random voltage, all of the voltage regulators on the board. So let's take a bit more of a closer look at the ones that I could actually identify and actually care about, like VCore, which is big and important. So VCore, the VCore VRM here is 1, 2, 3, 4, 5 phases. That right there, makes up your one phase. So you have this chip right here, which is a ISL 99227B 60 amp smart power stage, and these are stupid expensive. Like, as far as smart power stages go, you can't well, actually power stages in general go, but the smart power stages are generally more expensive in the first place. So, you can kind of ignore the like, if you say most expensive smart power stage I'm aware of, it also covers all the other power stages as well, because nothing's really more expensive than smart power stages to begin with. But yeah, these last I checked, these were going for $5 a piece if you were buying them in bulk quantities of like 50,000. Okay? So these are freaking expensive. Now, admittedly, there's not that many of them on this board, but for comparison, like, none of the other ITX boards I can think of have, like, well, some of them don't even use, like, smart power. Well, most of the other ITX boards don't even use smart power stages. The ones that do use power stages don't use power stages anywhere near this expensive. So, yeah, Asrock likes to splurge on their componentry. Like, that's something that's kind of consistent with their high-end boards, which I guess this is what you'd consider a high-end ITX, which is kind of awkward because you just can't fit that much stuff on an ITX board in the first place. So they always come out kind of imbalanced as far as I'm concerned. Like, oh yeah, it's a really nice board, except well, the VRM is really small, so that's potentially a minor that's potentially a concern. But still, on a lot of Asrock's high-end boards, you get some really top-end components, and well, price point wise, this isn't high-end, but it's the most expensive ITX board you can get. and it reflects it with the component selection right there. And these are called smart power stages because they integrate current monitoring, which is more accurate than some of the previous current monitoring systems integrated into voltage regulators. They also integrate temperature monitoring and a bunch of safety features like overcurrent protection and over temperature protection. So it makes them really hard to blow these up because if they get too hot, they shut down. If you push too much current, they shut down. If you short them out, I do believe they also shut down, which is kind of neat. So they also include a couple different fault protections for various, if the OCP and OTP don't save you, or you do something stupid and short them out, they should still, they should still not blow themselves up when that happens. But yeah, so that makes them smart power stages. And also, these are ridiculously expensive for a couple reasons. So they're smart power stages. They handle 60 amps, but they're also a reduced pack. Like, they're one of the smallest package sizes you can get for 60 amp power stages in general. Like, if you compare these to so these are 5x5 millimeter, or the package is called like 5x5 something, but I just remember that they're 5x5, roughly 5x5 millimeter squares. But for comparison, a international rectifier 3555 or a 3575, which are, power, those are high-end 60 amp power stages from international rectifier. Those are 6x6 millimeter. So these are reduced package size. Then they have this metal tab right here, which really significantly improves their, significantly reduces their thermal resistance to the top of the from the silicon to the outside of the MOSFET, because that is a direct metal connection to the actual silicon inside it. That connection is also hot. You get voltage on that. So if the phase is running, you get 12 volts max on that. If it's not running, you're still going to have V-core sitting on there, because that's literally hooked to the output of the... that's the actual switch node of the phase. I finally remembered what it's called. Yeah, so that's the switch node of the phase right there. So there's voltage on that. So that's not grounded. You really don't want to short that to like a heatsink or something. But basically that adds manufacturing complexity to the casing, so that makes them more expensive, and just they're also smart, and that makes them expensive as well. So that's why they're some of the most expensive power stages you can get right now. Is just they're small. They have the thermally, let's just call it thermally enhanced package. And they handle a lot of current, and they're smart. So that's why they end up being really, really expensive. But on this board, that actually works in its favor, because it does mean that out of the Z390 ITX boards, this one has one of the highest VRM efficiencies out there. So for 1.35 volts output at 500 kilohertz switching frequency, you're going to be looking at the following VRM efficiency figures. So 100 amps, which is, like a maxed out 9600K, you'd be looking at only about 9.5 watts of heat, which the cooling system that this board comes with should handle should handle perfectly. Like, it should have no problem with that whatsoever. Unless you have a, computer case that's the equivalent of a pillowcase. If you start, the thing is, your VRM can be as efficient as you want. If you if you intentionally hotbox it, it's gonna get hot, right? Like, if the heat has nowhere to go, even if you're producing very little heat, it'll just pile up over time. So that's kind of that. Anyway, going up to 150 amps, which is, a little past 150 amps, a 9900K becomes really impossible to cool for AIOs. So this is sort of the upper limit of reasonable cooling. At that point, the VRM will be producing about 16.5 watts of heat. And then when you go all the way up to 200 amps output, it'll be producing about 26 watts of heat. Now, 200 amps is sort of the theoretical limit for what you can do on a 9900K at ambient, because that is equivalent to like over 5 gigahertz core clock at around 1.4 volts V-core running Prime 95 AVX. Okay, so that is as hot as it gets. Now, the thing is, this is actually so damn hard to cool that unless you have like direct die and a full custom cooling loop, you're probably not gonna you're not gonna be able to hit that. But if you did have a cooling system that is capable of cooling a 9900K, pulling close to 300 watts, this VRM will actually be, well, better off at handling it than any of the other ITX boards. For comparison's sake, the MSI and the Gigabyte board do 200 amps output at about 40 watts VRM thermal dissipation. So like 40 watts coming off of the MOSFETs instead of 26. So yeah, it kind of like your efficiency is great when you spend like way too much money on your power stages, isn't it? Anyway, moving up, we go to 250 amps, and at this point we're going, sub-zero, and we're mostly considering these because technically these are 60 amp power stages. There's 5 of them. Theoretically, they should go all the way up to 300 amps. So 250 amps, you'd be looking at about 39 watts of heat. And at this point, you'd be looking at least like dry ice cooling. Okay, like you're not doing this on ambient cooling whatsoever. And then going up from 250 amps to the absolute theoretical sustained current output limit for this VRM, you'd be looking at about 58 watts of heat. Which is still not terrible. The main concern here is that since this is just a 5-phase, and these are 5x5 millimeter power stages instead of like 6x6, this VRM does not have a lot of surface area to start with. So this thing is ridiculously thermally dense, and you will notice that a lot of the other board vendors like Asus and MSI, for their ITX offerings, they actually split the VCore VRM into 2 separate sets of phases so that they don't have, potentially, like, you're not realistically going to hit this, but if you did, you have 58 watts of heat being generated, like, just there. That's literally where all 58 watts of heat come from. Now, admittedly, that's still a lot less heat heat density than your average CPU, but your average CPU has a much bigger cooling system than, what even this motherboard comes with, which I rather like the cooling system this has. So, anyway, let's talk about the cooling system. Because, this might actually be viable for benchmarks on LN2. Though I think a 9900K might be able to peak just above that, potentially. Not 100% certain on that, but still, like, on ITX boards, you're not getting a more powerful VRM than this. Like, that's just a fact. It's just, even with how powerful this is, the fact that it's, 5 phases jammed right next to each other, and it's ITX, this is not exactly ideal for providing 300 amps of current, even if the power stages could theoretically do that just because of the thermal density. Anyway, let's move on to the actual cooling system that Asrock has on this board, which is quite substantial. So that's the heatsink assembly. This right here, that goes right on top of the VRM, and it has a lot of fins. We're going to take a closer look at that. We have a heat pipe going from that to this thing right here, which that sits on top of the chipset and is actually the chipset heatsink. So potentially what might happen is if the VRM gets really hot, it'll actually start heating up the chipset, which could be an issue, right? I'm not sure what the temperature limit for the chipset is, though I would also assume that, like, after the heat pipe, you wouldn't be looking at anywhere near whatever the MOSFETs are hitting. And hopefully Asrock doesn't have the temperature limit set to where, like, the OTP on those power stages trips at 140 degrees Celsius. Like, hopefully the temperature limit is set below that, right? Because if the power stages are at 140, well, this whole heatsink assembly could potentially be quite close to that, depending on just how bad the airflow situation is. Anyway, the other concern I kind of have with this right here is that your M.2 actually goes inside of that. So it might be possible. Now, I'm not going to be able to test this. I don't have any M.2 drives, but like one thing I'm kind of concerned about is like, well, could the VRM maybe cook the M.2 SSD? Is just one minor like concern that, it's just like, well, I mean, it is dumping the heat right under the M.2 SSD, so that seems like a potential hazard, but yeah, we'll see. Like, ultimately, what I can test is just stick a thermal probe on this, and if this doesn't get all that hot in the first place, then it's like, well, the M.2 SSD should be fine. Anyway, this right here is the actual M.2 heatsink from underneath, and we'll take a closer look at that right now. So that's what and I just screwed that up. So that's the actual M.2 heatsink. And I gotta say, this is one of the ones where I'm like, well, this actually has surface area compared to the usual slab of metal that you get on most other motherboards, which really would act more like a thermal buffer than an actual heatsink. Because if you're not adding any surface area and just add a bunch of mass, you're just you're literally just delaying the inevitable. Because yes, the heat is gonna soak into the block of metal, but it's not gonna go anywhere from said block of metal because it's a block of metal, not a heatsink. This actually has some finnage on it, which actually makes a pretty significant difference to the surface area if you think about it. Like, these fins look really small, but it's a big step up from just a flat block. So yeah, this is definitely not the worst M.2 heatsink I've ever seen. And it actually could be quite effective. And next we have... Oh yeah, also, I just wanted to point out that on a lot of motherboards, what I've noticed with their like VRM heatsinks, when they have heat pipes, they'll have the heat pipes just like pressed into the aluminum, and there won't be any actual thermal interface material. But we can clearly see here what looks like thermal adhesive. That doesn't look like solder, so it's probably thermal adhesive. That's certainly better than just having the heat pipe stuffed into there, because I have seen boards where that's actually been the case, where the heat pipe wasn't actually like, there wasn't any thermal interface between the heat pipe and the heatsink. It was just kind of there, and it's like, well, I mean, I guess it'll transfer some heat, but it could certainly be more efficient. So, you know, Asrock is actually doing that right here, though that might be more concerning for the chipset at that point. Because it makes it easier for the VRM to potentially cook it. Anyway, and here we have the side of the VRM heatsink. And I gotta say, because of how this VRM heatsink, so it's not installed on the board right now, so you can't see it. But normally the way this works, like the reason why there's this cutout right here is because the USB ports end up under there. There's actually quite a lot of space under there. And so I was thinking, you know, if they wanted to really maximize the cooling potential of this heatsink, they could have added some more fins right here. And at that point, you might be like, but Buildzoid, there's an I/O plate right here. You know, that, well, you have an I/O plate that kind of runs like that along the board, right? And that's just going to block any heat that gets dumped into the air that's down here. It's just going to get stuck there because the I/O shield, solid heatsink, small gap, right? So if any heat that gets dumped in there wouldn't actually go anywhere, but I was thinking, you know, they could have just put holes in the I/O shield in that area so that the heat could eventually escape. The other thing I was thinking about is that, you know, it might potentially make sense to just run this motherboard without the I/O shield completely, because that should help the heatsink with shedding heat to outside the case, which is ultimately where all heat ends up anyway. So yeah. Anyway, so that's the VRM heatsink, and it, like, you know, we do have actual fins with lots of surface area here. So this is by far the most high surface area heatsink I've seen so far on the ITX boards. The one thing worth noting is these gaps are actually pretty small, so getting airflow into them might be a bit more difficult, but it seems like there might be a pattern to the width of these gaps relative to their depth, to try compensate for like the airflow restriction that you get from, because if you put the fins really, really close together, well, no air is actually going to get in between them, and no cooling is going to happen, right? Like, there's not going to be any airflow through fins that are just jammed right up against each other, even if you have a lot of them. And that's kind of like, now looking at the fact, like, this gap is a lot wider than this gap, and this is a lot deeper. You know, that looks like that might be some of the motivation behind that. It could also just be a stylistic choice, but still, this looks like a heatsink that should be more than capable of handling the significantly less heat that this VRM produces compared to a lot of the other ITX boards that I've tested so far. So, yeah, also one thing I was thinking was, since this M.2 heatsink, if you don't have an M.2 SSD, right, that heatsink actually makes contact with this plate right here, and that, and also this. Except normally, there's no thermal interface material right there, so I was thinking, you know, you could potentially try and improve your VRM thermals by just putting thermal paste right there, and there, and there. And then when you put this on, right, you increase the surface, like, well, you make the thermal transfer through that heat pipe, like, it'll be VRM heatsink into heat pipe, into chipset heatsink, into thermal paste, into this, but you'll make that thermal transfer potentially more efficient, and you'll basically get potentially more VRM cooling, which I think I will test that because that just seems kind of random and interesting for me to test. So we'll see if that makes any difference. Like putting thermal paste to connect the M.2 heatsink to the chipset heatsink. But yeah, so the VRM cooling system on this thing, it's quite elaborate. And considering that this, like the nice thing is this VRM produces way less heat than all the other boards so far. So, this has more surface area. It has a heat pipe. Admittedly, that heat pipe doesn't actually go to anything with, significantly more surface area. But I think this VRM right here should get the absolute best thermals of any ITX board I've tested so far. Especially considering the cooling system that it comes with. So, let's move on to other things. The iGPU VRM is just more ISL 99227Bs. Unfortunately, I've not bothered to check how much power the iGPU pulls doing anything, so I can't really talk much about that. But there's two 60 amp smart power stages in that, which in my opinion is there's no heatsink on them. So I guess the justification for doing that is like, yes, your iGPU VRM is probably, like, this is probably a more expensive iGPU VRM than what you get on, like, any other... Oh, no, the X290, the Z390 Dark has the exact same iGPU power delivery setup. So, okay, no. This is probably tied for having the most expensive iGPU VRM with the Z390 Dark. Because a lot of the other boards, for their iGPU VRM, it is still two phases, but they just opt for, like, two dual NFETs or just discrete MOSFETs or just, like, whatever random cheap MOSFET they can get. So that it's, like, technically the iGPU can run. I wouldn't recommend, like, I don't know if you would actually want to overclock it with that, but it will power the iGPU at stock at the very least. So, yeah, so this seems a bit generous, but at the same time, this doesn't actually have a VRM heatsink there, so... it might be mostly to make sure that this doesn't overheat, even considering that there's no heatsink there. So, still seems kind of overkill. It could have probably gone for like 40 amp smart power stages and it would have still been fine. Or just regular power stages from Intracell that are 40 amps and it would have still been fine. But, yeah, so that's our iGPU VRM up there. Then for VDDR, we have unfortunately, I can't identify the controller for this, but this is a single phase. And that chip over there is an SM7341 from Sinopower, and this is a dual NFET, and it's a really, really nice dual NFET. So it integrates both the high side and the low side. And I don't think that they're running it on straight 12 volt. Like I doubt they're using 12 volts as drive voltage for this, because even if you run it on 5 volts, it's a ridiculous overkill for memory power. Anyway, at 5 volts gate, I really screwed this up. I don't have enough space. We're gonna fix that. There. SM7341, so dual NFET, and the low side, no, let's go with high side first, because that's the one that handles the 12 volts. High side is 6.5 milliohms at 4.5 volts gate to source, so, 5 volts gate to source as well, that would work out. And then low side is actually 2 milliohms. And that's actually, like, 2 milliohm low side is better than what a lot of motherboards use for their VCore VRM low side MOSFETs. Which, the good news is this memory VRM will never overheat. The thing is that makes me very concerned about some motherboards out there. It's like, wait, you can put this in the memory VRM, but you can't put this into the VCore? Really? Like, what? Why wouldn't you do that? Anyway, so yeah, this is ridiculous overkill for memory power. That kind of covers the power capabilities of the actual regulators. Now then, let's take a look at the capacitors on this board, because this is another thing that, like, Asrock likes to splurge on, I assume, because they have the highest rated, like, in terms of thousands of hours, Asrock's capacitors are the highest rated out of basically any other board vendor. And that goes for, like, all of their aluminum polymers here. So like this right here, we can clearly see this is a 12,000 hours rated Nichicon FP series capacitor. So, and that's basically like Nichicon is the standard for high-end, like for capacitors for high-end motherboards. The only board vendor that doesn't use them right now is like MSI. Well, and then board vendors that I don't consider worth buying motherboards from, right? Like BioStar. Well, I'm not actually, BioStar might also use them, but I still wouldn't buy a BioStar motherboard. Anyway, so these are Nichicon FP series capacitors, so aluminum polymers, 12,000 hours rated at 105 degrees, which, I mean, you shouldn't be running your motherboard at a temperature where your capacitors are at 105 degrees, but at least this will last like more than 2 times longer. Like these caps will last more than 2 times longer than everybody else's, because generally most boards opt for only like 5,000. And then there's a couple boards that go for 10,000, but a lot of the time you don't see anything rated, like most boards don't go past 5K. And then like the sort of the lowest, like the cheapest capacitors you could buy are like 2,500 or 2,000 hours. Anyway, so these are rated for 12,000 hours, so, you know, they should last forever. And they're also 6.3 volts, which is, that should actually improve their endurance rating even further, because VDDR normally sits at like 1.2 to maybe 2 volts. So if you have a significant headroom in your voltage rating, that actually improves the lifespan as well. But the one thing that I kind of notice here is that these, for the memory VRM, for the vCore VRM, this is not really a concern. But there are, like, you know, if you look at ATX boards, you obviously have more bulk capacitors on the output of the VRM. So, you know, that's just something, like, these are primarily for transient handling load to idle transitions for transients. So, as well as actually from idle to load transitions as well. But yeah, there's not that many of them compared to like a full-size ATX board, mostly because there's just not enough space. So that sometimes, like, that makes me wonder with some ITX motherboards is like, could you add capacitors and it would make it better? But there's some stuff on the back of the board that we'll also get to. But with the memory VRM, here I'm actually more concerned about it, because there is literally just 2 bulk capacitors in the entire memory VRM. And I guess they might be then running this MOSFET at like stupid high frequency to compensate. Because that would, you know, achieve that effect. But and then the ridiculous spec would also make sense. I guess I'll check that when I have the board running. But the thing is normally, even on like 2DIMM motherboards, if they're geared for memory overclocking, you're going to be looking at like, you know, maybe 3 bulk capacitors right off of the memory VRM, and then you're going to have another 2 between the DIMM slots and the CPU. We only have 1, and the ones we do have aren't even that high capacitance to start with. They're just 560 microfarad. And the other thing is that 12,000 hours rating, normally you can't get the lowest ESR or the lowest ESL in the highest endurance rating. Like, endurance rating generally means you're like, you can't get the highest performance capacitors. Those don't tend to last quite as long as the high endurance ones. So yeah, that, like, I expect this motherboard to absolutely kill it on memory overclocking anyway. It's just something I'm wondering about, since I do own this motherboard. I'm free to do whatever I like with it, right? I can mod it. So it does make me wonder, is like, well, could it be better at memory overclocking? Because I have seen, you know, other people overclock with this motherboard, and I've seen some absolutely incredible memory overclocks come out with this board. So as like, well, what if you brought the memory, like the output filtering for the memory VRM up to the same standards that you would get on like an ATX board? Would that give it, I don't know, 50 megahertz more memory clock? So yeah, that's definitely something I'm considering, just looking at the fact that these are, you know, 560 microfarad, 12,000 hours rated capacitors, and there is only 2 of them on the entire memory VRM. The vCore VRM I'm not that concerned about, because we have a good amount of phases. They can support a pretty high switching frequency, but memory VRM, because the other thing is a lot of boards, like Asrock tends to also like to do 2-phase memory VRMs, which is the other way. You can go up in switching frequency, or you can add phases, and both of them will sort of achieve the same effect at reducing your output ripple, and give you better transient response handling if you're voltage controller is smart enough for that. So yeah, that's just something I'm thinking about, since I, can kind of do whatever with the board after I'm finished testing it, or as part of testing. Anyway, the other thing I wanted to draw attention to on the back of the board is, you can do that, is these guys. So I have noticed that, like, I noticed these before on the X299 OC formula I have from Asrock, and these are big freaking multi-layer ceramics. And the reason why I draw attention to this is these are 1206 package. Okay, and I actually pulled one of these off and checked what capacitance it is, and it's 68 microfarads. And the reason why you don't normally see big multi-layer ceramic capacitors like this is because these things are really freaking expensive compared to, something like that. And even in the 68 microfarad size, these are still pretty expensive. These were like I was just looking at DigiKey, and they were still at like $0.2 if you were buying them in bulk. Actually, no, I think it was 0.2 pounds. I'm not sure what region my DigiKey was set to, but it was 0.2 of some like major currency. So not exactly what you would consider cheap. Now, the interesting thing is that Asrock does seem to be like it replacing, like normally the back of the CPU, you just get a whole bunch of like 0805s or 0603s. And Asrock here, they just have, a couple 1206s. But these are pretty expensive. And I'm pretty sure the total capacitance of this is higher than what you normally get with a bunch of 10 microfarad 0805s on most motherboards. Also, they're using them just for like the VCCIO and VCCSA rails by the look of things as well, because, well, on the other side of the board, there's just kind of not enough space for, bulk capacitors in this area. Because honestly, actually, oops, heatsink keep out zone right there is already a concern. And so, yeah, here there's just not enough space. It's kind of interesting that they didn't just opt for some, SMD polymers or something on the back here. Because they did opt for that with the iGPU VRM right there. So we have those, which there is only 2 of them. And I do find that kind of concerning because that looks like nowhere near enough. But I don't overclock iGPUs, so I don't really care that much either. So, yeah, but I did want to point these out because you don't really see these every day, and it's just kind of interesting that Asrock is using these, whereas a lot of other board vendors don't go with any, they're the first board vendor I've ever seen use capacitors like this. So, yeah, that's just kind of neat, in my opinion, where it's like, oh, that's new. I've never seen that before. And then on the other side, what's kind of interesting, because obviously if you have the large 1206 68 microfarad capacitors on the back of the CPU socket, well, those aren't exactly going to be the best at handling very high switching frequency noise from the CPU itself, which is why if you actually look at the back of the CPU, you have the super tiny like 0201 multi-layer ceramics directly on the CPU. And then, as you get steadily further away from the CPU, you'll notice that the capacitors get a bit bigger every time. So in the CPU socket cavity, you normally get like 0805s, 0603s. Some board vendors like to mix it up where they'll have like a mix of 0402s, 0603s, or 0805s and 0603s. Well, Asrock's gone for 0603s and 1206s on the back, which is... that's just an interesting combination, in my opinion. I did not pull one of these off because they're in the middle of the bloody socket and I don't want to break any pins. But, yeah, so that's just kind of interesting how, you can even see just differences in the output filtering for the V-core and actually associated rails as well, because, this right here does not, I assume that's like VCCSA or VCCIO or something like that. This is probably iGPU, just based on where it's located. And you can kind of see there's a separation in the power plane right there. But, as well as down here. But, yeah, it's just kind of interesting that, the differences you have between even just the output filtering inside the CPU socket itself, right? Between the different board vendors. So I did want to point that out. And Asrock's approach seems to be not necessarily the most cost-effective, so I hope it's optimized for performance. Because those, if you just went with a bunch of 0805s, I'm pretty sure it would be cheaper than those 1206s. You maybe wouldn't get as much total capacitance, though. So... yeah, interesting decisions right there. Um, oh, and then, do they actually have an input filter on the 12-volt rail? I'm just going to check something. I don't really see one. Okay, well, that's kind of standard for ITX boards. No, that's not a lot of 12 volts. But they do have 5 phases. I'm just like, if you saw like a full ATX board, it would be normal to have a lot more bulk 12 volt well, these are on the 12 volt power plane, so they're there to smooth out the switching noise from the MOSFETs towards the power supply. And in that department, we seem to be both missing the input filtering inductor, which just is God, because there's not enough space on this board. And then we only have, in total, yeah, just 4 bulk capacitors in total in the on the back of the VRM. So it's kind of interesting as well, but that's kind of just a restriction of, you know, it's an ITX board, it's too small. But I think I still have a bunch of 16 volt tantalums that I pulled off of a dead GPU. So I might just, you know, like if I'm going to be modding this board and just modding everything else, then I might as well just mod that too. Because why the hell not at that point? So yeah, that is it for this PCB breakdown. My God, this is a long one. Anyway, that is the Asrock Z390 Phantom Gaming ITX. And I mean, like, physically, you basically can't fit any more anything on this. So, and in terms of the actual component choices, I don't really see any issues with anything that Asrock has gone for here. They have definitely one of the most elaborate VRM cooling systems that I've seen on an ITX board so far. So I'm really excited to see how this does in testing, because I expect some, you know, awesome results from this. Like, you know, I would not be surprised if, well, no, I would still be surprised if this handles and maxed out 9900K, just because that is a lot of power consumption. And, you know, well, it should handle it with significantly less fan RPM than all the other boards I've tested so far, but I don't think it'll get away with like a 0 airflow scenario quite yet. Mostly because this VRM is kind of cramped, but I don't know, maybe the heat pipe does magic for your thermal density. And then everything else on this board, I mean, like all the issues I can see with this board are basically down to the fact there's just not enough space to do anything. It's ITX, like you can't physically fit much more on here. And Asrock's definitely done their best to fit as much as they possibly could to, you know, like with those. As well as the 1206 multi-layer ceramics, which are expensive as hell. So, yeah, at this point, you know, I kind of can't wait to actually get around to running the board, because physically, I really, really like this thing. Now the main concern is just like, will I like Asrock's mainstream BIOS, considering that I don't like their Ryzen one, I don't like their cheap one, the one they have on cheap Ryzen boards, I don't like the one on X299, and I definitely don't like the ones that were like, you know, AM3 Plus and older. Those BIOSes are probably some of the worst BIOSes I ever dealt with. So yeah, anyway, that's it for the video. Thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. Also, huge thanks to the guy who actually paid for this board, because, I mean, that gives me the freedom to fantasize about things like, what if I fantasize and probably follow through on thoughts like, what if I whacked capacitors everywhere on this thing? And what was there? Right, if you'd like, one last thing, if you'd like to support actually hardcore overclocking, I have a Patreon. So, you know, you can donate monthly through that. Or if you'd like to buy some merch, there's shirts, stickers, posters, socks on the AHOC Teespring store. There are links to both the Patreon and the store down in the description below. They help out with running the channel immensely. And yeah, it'd be awesome if you would check those out. Thanks for watching, and goodbye.